So this video covers section 4-2, which is pages 32 through 35 in your note-taking guide. And in this section we're going to look at some basic probability terminology and some different ways that we might represent probabilities. So to start off here on page 32, an experiment is an activity whose results can be observed and recorded. So in class last time, the experiment that you guys were performing was rolling these two dice. One student had die A over here in the corner, and the other student had die B. So an outcome of an experiment is each possible result. So one outcome might be that die A rolled a 4. Another outcome might be that die B rolled a 3. Another outcome might be that die A rolled a 0. So the sample space is the set of all possible outcomes. So this would be every single possibility. And we're going to talk in a minute about the best way to represent the sample space. We might organize this in a table, or you might list out all the possible options. And an event is any subset of the sample space or a collection of outcomes. So the sample space would be every single outcome, and an event would be a subset of that, or an outcome of interest, you can think of it as. So I want to now look at this notation that we have down here. So in blue here, I have P open parentheses, close parentheses. So this stands for the probability of. Then inside the parentheses in red here, I have A greater than B. So what's inside my parentheses is going to be the event of interest. So here, A bigger than B, well, that would be the event that die A rolled a number that was larger than die B. So in this case, B always gets a 3. So the probability that A rolled a number higher than 3. Well, we can look here, and there are 1, 2, 3, 4 out of 6 places die A was greater than die B. So that would be 4 out of 6. So this answer here, this is going to be my numerical probability. So I want to look at some examples of this notation here. So here I have, what is the probability that B equals 5? So if I look over here, here's die B, it's all 3s. So what's the probability that I rolled this die that has only 3s on it and that I get a 5? Well, that's impossible. So we would represent that with 0. So the probability of 0 down here on the number line would be an impossible event. So next we might look at, well, what's the probability that B rolls a 3? Well, B always rolls a 3. So this would be a 1. All right? So a probability of 1 would be for a certain event. So if you look here, as these probabilities get closer and closer to 1, they become more likely. So a probability close to 1, so 0.99, that would be almost certain. A probability of 0.001 would be very unlikely. So we looked at two kinds of probabilities last time. The experimental probability, also called the empirical probability, is determined by observing the outcomes of an experiment. So this is when you guys actually rolled the dice, and you might have had tally marks or identified how many times die A won as opposed to how many times B won. And you could calculate this probability. It is the number of the times. So this here, this probability of X. X is the event I'm interested in. So if this is going to be the number of times X occurs divided by the total number of times the experiment is repeated. So this was when we actually performed the experiment and rolled the dice. Well, after a while, most of you guys stopped rolling your dice because you saw that die B always got a 3, and you guys jumped to what we called the theoretical probability. And this is the probability under ideal conditions. So this would be the number of ways X can occur, and we're going to divide by the total number of possible outcomes. So in the case where, for example, let's look over here, if we want to know the probability that A equals 4, right? Well, the number of ways X can occur, well, how many ways can I get a 4? Well, there's 1, 2, 3, 4 over the total number of outcomes. Well, how many outcomes are there? Well, there's 1, 2, 3, 4, 5, 6. So there is 4 out of 6 would be my theoretical probability. So last time we then moved to a little more challenging problem. Now we were interested in, well, what's the probability that die C rolls a number greater than die D? Well, this one got a little more complicated because in our first example and our second example that we looked at last time, die B was always a 3, so it wasn't that difficult. Well, now let's look here. The sample space for die C, I could get a 2 4 times and then a 6 2 times. So my outcomes here might be 2, 2, 2, 2, 6, and 6. Then when we look at die D, well, that has 3 1s and 3 5s. So now we want to find the sample space, and this notation here, C, you might think of this as multiplied, but it's red cross. So C cross D. This is going to be pairing each, up here, each outcome of C would be paired with all my outcomes here, and so forth. So the sample space is most easily represented in a table. So here I might have 2, 2, 2, 2, 6, and 6. And down here I could have 1, 1, 1, 5, 5, and 5. So if I look at this example, if C rolled a 2 here and D rolled a 1, well, C would win because 2 is bigger than 1. Right? Well, what if C rolled this other 2 with a 1? Well, C's still going to win. So C would win here, here, and so forth. Then if C rolled a 2 and D rolled a 5, well, in this case, D would win. So if I wanted to find the probability that C was greater than D, well, I can count up in my total sample space here. I would have a total of 36 outcomes. And the ones I'm interested in, my event of interest here is when C is bigger than D, so we could count these. So that would be 24 of these 36. And this would reduce to 2/3. So that's one way that we found a probability, was to draw out the entire sample space. And the sample space most of the time can be represented in a table. Some of you guys noticed is here there were a number of ways that C could win. C could win if C got a 2 and D got a 1, or if C got a 6 and D got a 1, or if C got a 6 and D got a 5. So you said, well, there's 3 different cases where C wins, but there's only one way that C loses. The only way that C can lose was down here where C rolled a 2 and D rolled a 5. So some of you guys said, well, it's easier for me to see when C loses as opposed to when C wins. So what you guys did was find the complement of the event. Right, so the complement with an E here, not an I, is denoted with a bar. So the complement of A would be A bar, consists of all the outcomes in which A does not occur. So this was like, for example, the complement of winning would be losing. These two events are complementary. So if I didn't win, I know I lost. You might think the complement of men would be women. So if I tell you a given student is not a man, well, you know that she is a woman. Right? So the complement of being present would be being absent. Right? So if I say, I know that student John is not present, then we know that this student John is absent. Or if you think of the case here, let's look at die C. If I said die C is 2, well, the complement of C getting a 2, if I said I know that die C did not roll a 2, then die C rolled a 6. So in order for two events to be complementary, we have two criteria. They must be mutually exclusive. Right? And by mutually exclusive, we mean cannot happen at the same time. Right? So there is no overlap. Okay, so if we look down here at our examples, we can't both win and lose. We can't be both a man or a woman. We could not be both present and absent. And I couldn't roll both a 2 and a 6. So they're mutually exclusive in that they can't happen at the same time, or they do not overlap, and they are also exhaustive. Right? And by exhaustive, we mean we cover all our options. So our only options here are to win and lose. Our only option is to be a man or a woman. Our only options are present and absent. So by cover all your options, think about if I had a standard die that was numbered 1 through 6. Well, here, if I had a regular die, rolling a 2 and a 6 would not be exhaustive because there's other options. Maybe I rolled a 3, maybe I rolled a 5. So by exhaustive here, we mean there's only 2 options and we've covered both of them. So if I know that I'm both mutually exclusive and exhaustive, then we know these are complementary. So if 2 events are complementary, the probability, let's say that I win, plus the probability that I don't win, well, I've covered all my options and there's no overlap here, so this probability should always be 1. So let's think about those examples we looked at. What is the probability that I win or I lose? Well, those are my only options, so that's going to be 100% of the time. Or that I select a man or a woman. Well, those are my only options. that I'm either present or absent. So again, all of these, if two events are complementary, we know that the sum of their two probabilities is always going to be 1. So it's sometimes easier to find the complement than it is to find the actual probability. So here, if I want to know what's the probability of A, I might say, well, that's 100% minus the probability that A does not happen. And this is what a number of you guys did for this case. Y'all said, well, there's 3 different ways that C could win. All right, C could win here when it gets a 2 and D gets a 1. C could win when it gets a 6 and D gets a 1, or when C gets a 6 and D gets a 5. Well, you said that was too much work there, all those cases. So some students said, well, this is going to be 1 minus the probability that C loses. So you said, all right, well, this is 1 minus, where does C lose? Well, C only loses right here 12 out of 36 times. So this would be 24 out of 36, which is 2/3. So another way that we might represent this is with a tree diagram. I'm still looking at that same question. What's the probability that C is greater than D? Well, some of you guys, instead of drawing out this sample space, we're going to come back to this. Here, again, we could have a 2, 2, 2, 2, 6, and 6, or a 1, 1, 1, 5, 5, and 5. So we want to know, what's the probability that C is greater than D? Well, some of you guys said, well, we can reduce this here to 4 outcomes as opposed to 36. So you said D is either a 1 or a 5. So the probability that D is 1, well, this happens half the time. Or some of you guys said 3 out of 6 times. And D equals 5 happens half the time. Okay, then we come down here, well, when does C get a 6? Well, if we look here, C gets a 6 2 out of 6, which is 1/3 of the time. And C gets a 2 the remaining 2/3 of the time. So we want to know when C wins. So if I get a D gets a 1, C gets a 6, well, C is going to win right here. If D gets a 1, C gets a 2, well, C wins again. And if D gets a 5, C gets a 6, C wins. And the only case where D wins is going to be if D gets a 5 and C gets a 2. So here, let's see if we can find this probability here in blue that D wins, and I'm going to do 1 minus the probability that C is less than D, just like we did on the previous slide. D equals 5 half the time. So let's look where D equals 5. Think of this as a fraction here. If this is my whole, D equals 5 half of the time. So this happens here. So next I want to look at, when does C get a 2? I can divide this piece up into thirds, and we get a 2 2/3 of the time. So now I'm interested in, when do both of these happen? Well, when does D equal 5 and C equals 2? Well, that's these 2 blocks right here. So that's going to happen 2/6 or 1/3 of the time. So therefore C wins 2/3 of the time. So again, we get the same result. This is just another representation. We might use a tree diagram to represent our probabilities. Now don't get bogged down in how I got this 1/3 here. We're going to come back to this in the next section. Hopefully this picture makes it obvious. This is 1/3 or 2/6 of the time, but we're going to come back to this in a minute. But what's important that you understand today is just this representation, this tree diagram. My first event happened half of the time here, and then my second event happens 2/3 of the time. So we can use this tree diagram to help us figure out when they both happen. So let's look at another example. I want to construct this tree diagram for the case when we're comparing die A and die D. So die A here could either be a 4 or a 0. So A equals a 0 1/3 or 2/6 of the time. And then A equals 4 4/6 or 2/3 of the time. So next I'm going to look at my next event. D here could equal a 1 or D could equal a 5. So D equals 1 3/6 or half the time, and the other half of the time we are a 5. So now we want to know, when does D roll a number greater than A? So when does D win? Well, if A gets a 0, D wins right here. If A gets a 0, D wins again. If A gets a 4 and D gets a 1, nope, A wins there. And if A gets a 4 and D gets a 5, D wins here. So again, we see the same case that we just saw in the last example. I could find all these different ways that D wins, but it might be easier, the probability that D is greater than A, well, it might be easier for me to do 1 minus the probability that D is less than A. Or find the complement here, because there's only one place where A wins. So here, 2/3 of the time I get a 4, and of that 2/3 of the time, half of the time I get a 1. So let's see if we could draw out a little diagram here. So let's say, here's my little fraction bar. Alright, and 2/3 of the time A equals 4. So this is going to happen 2/3 of the time. Now, of this 2/3 of the time, half of the time D is also going to be a 1. So what's half of this 2/3 here? Well, if I took this 2/3 and I cut it in half, that's going to be this piece. So half of 2/3 would be a 1/3. So this is going to be 1 minus a 1/3, which is 2/3. Now again, don't get bogged down in this 1/3 again. We're going to come back to this in the next section, but what I do want to make sure that you understand is how to represent this experiment with a tree diagram. So we've looked at the sample space for finding a probability and a tree diagram. The last representation I want to look at is called a contingency table. And this is just another way of organizing all of your outcomes. So what we're going to do, I'm going to look at the same problem, die A versus die D, and see if we can fill out this contingency table. So we're saying, under perfect circumstances, how many times do you think A would be a 4, so I'm right over here, and A be a 0 if I rolled these dice 36 times? Well, we said, well, let's suppose I just roll it 6 times. I would get 4 4s and 2 0s under perfect circumstances. Well, let's say I rolled it 12 times. Well, if I rolled it 12 times, I would think I'd get 8 and 4. So here, to find out how many times I'd get a 4, well, I want to know what is 2/3 of 36. And how many times I get a 0? Well, that would be what's 1/3 of 36. So under ideal circumstances, I would think that 24 times I would get a 4, and 12 times I would get a 0. So I can fill in my table accordingly. So let's do the same thing for die D. It's a little easier. So half of the time I'm going to get a 1, half of the time I'm going to get a 5. So what's half of 36? Well, that's a little easier. This one's going to be 18 and 18. So now the tougher part is we need to fill in this table such that when I get a 4 and a 5 and a 0 and a 5, these two cases are going to add up to 18. And when I get a 4 and a 5 and a 4 and a 1, these are going to add up to 24. So let's say now I'm looking at this 24, and I'm going to come to die D here. Well, half of the time I'm going to get a 5, and half the time I'm going to get a 1. So here I want, let's see if I can draw a little arrow here. Well, what's half of 24? Well, I should get a 5 12 times and then a 1 12 times. So we can do the same thing here with our case where we're 0. 12 times we got a 0, and then half of those 12 times I should get a 1, which is 6 and 6. So this is going to be half of 12. So once we construct our contingency table, or oftentimes in the book you're given the contingency table, now we can ask that question, well, when is D greater than A? Well, D is greater than A here. D is greater than A here. And D is greater than A here. So here we have 24 of my 36 options, which is 2/3. Now most of what we've done today has been a review, but now here I'm going to pose this extension problem. This one is a little tougher. So here we're going to pick one die and play this die against a randomly selected second die. So you get to choose which die you want, and then I'm going to close my eyes and pick one of the remaining dice. Say which die has the greatest probability of winning against a random opponent. So I'm going to get you started here. Here, let's say I pick die C. So I pick C. All right. So the first thing, we have 3 cases of who my opponent can be. You could pick A, you could pick B, or you could pick D. Now this is random. You're just going to close your eyes and pick, so this would be a third, a third, and a third. You roll your die, and you could get either A could be a 0, or A could be a 4. Well, this happens 1/3 and 2/3 of the time. Well, if you pick B, this is an easy one. B is always a 3, so that happens 100% of the time. Next, D could either be a 1 or D could be a 5. And this happens half the time and half the time. Now, why this one is an extension problem, I'm going to leave it to you to finish. Well, we still don't know what I rolled. I rolled the C. So here, C, we have more cases. C could be a 2, or C could be a 6. And this happens 2/3 and a third. So I'm going to leave it to you to finish this. So what's the probability that C wins? Well, where does C win? If I get a 0 and a 2, C wins here. 0 and a 6, C wins. A 4 and a 2, nope. A 4 and a 6, yep. A 3 and a 2, nope. A 3 and a 6, yes. A 1 and a 2, yep. A 1 and a 6, yep. A 5 and a 2, nope. And a 5 and a 6, yes. So we could find all of these probabilities separately and put them back together. I don't want you guys to get bogged down in this arithmetic right now. What I think is important for today is that you understand this tree diagram. Right? In the next couple of sections, we're going to talk about different ways to calculate these probabilities.